Hi kids, today we're going to talk about exponential and logarithmic functions, really just exponential today. So let's first look at some common numbers that we already understand. If I look at the number, if I look at this and I've got 2 times 2 times 2 times 2 is 2, this equals 64, right? 2 to the 6th, 64, I know what that is. So I take the number 2 and I get bigger and bigger and bigger. Every time I multiply by the number 2, I'm doubling something and obviously I'm getting bigger. However, if I take 3/4 and I multiply by 3/4 times 3/4 times 3/4, because I'm multiplying by a number that is less than 1, in other words between 0 and 1, I'm shrinking my number. I'm only getting 3/4 of it each time. So when I multiply across the numerators, I'm going to have 81, and across the denominators, I'm going to have 256. So if you look at this, you think, oh, what is that? Well, that's approximately, I don't have my approximately symbol here, but it's about, let's say it's about 1/3, okay? So I took the number 3/4, and I multiplied it by itself, kept going, and I wind up with something smaller. Okay, this is something you probably already know. Okay, so now let's take a look at exponents and what each of these little symbols means, the negative sign, the 5, and the 6. So when you look at an exponent like this, I want you to think about this stuff, these 3 things, as being instructions. And each one has a certain purpose, okay? So the negative sign is the thing that says I'm going to flip the fraction, okay? The 5 tells us that I want a certain power, and the 6 tells us that I want a 6th root. So I'm going to flip it, I'm going to have the 5th power, and I'm going to have the 6th root. Okay, so it doesn't matter what order we do those 3 things in. We just need to make sure we follow all 3 sets of instructions. So if I look at this problem, if I want to take 64 and put it to the 5th power, that's 64 times 64 times 64. I mean, we don't want to do that first. Instead, we want to do whatever's going to be easiest first, because these are all things having to do with exponents, so it doesn't matter which one we do first. All right, so the easiest thing to do is find the 6th root of 64. Now, obviously, this is something you do without a calculator. So I find the 6th root of 64, which is the number 2. Okay, because 2 to the 6th is 64. So I'm down to 2. Now, I've still got to flip it. So when I flip it, okay, that'll give me 1/2. Now I'm into fraction territory. Probably what I should do instead first is put 2 to the 5th power. So 2 to the 5th power is 32. And then the third thing I'm going to do, the only thing I have left to do, is flip the fraction. In other words, write the reciprocal. So my answer then, or the simplification of this, is 1/32. Okay, new problem. This time I've got a fraction to the negative 3/2 power. So let's write out what all of these numbers mean. The negative 3, the negative sign, the 3, and the 2. Okay, so the negative sign means we're going to flip the number here, the base, the 1/4. That's probably going to be a good thing to do first so that we get out of fraction territory. Then we've got this number 3. This is where the power goes, so we're going to have to take whatever our number is and make it to the 3rd power. Multiply it by itself 3 times. Then the 2 here in the denominator, that represents the root, so we're going to have to find the 2nd root or the square root. Okay, so again, if we think about what's the easiest thing to do first, I would probably find the reciprocal or flip the fraction first. So that gives me 4. Okay, then I've got to still cube the number, and I've got to find the square root. I think it's probably easiest to find the square root of 4 first. So that gives me the number 2. Then what do I have left? I still have to cube the number. 2 cubed is 8. Okay, so there's my number. 8 is the simplification of this 1/4 to the negative 3/2. Okay, so one more example. Here I've got negative 27. I'm going to need to flip it, which I'm probably going to do last. I've got to square it. Well, I don't want to have to square 27. And I've got to find the cube root. Well, 27 is a perfect cube, so I probably am going to want to do that first. Okay, So I want the cube root of negative 27, which is negative 3. Okay. Then I think about, all right, what's easiest to do next? I'm going to go ahead and square it next, which gives me a positive 9. And then last, I'm going to find the reciprocal, which is 1/9. Okay, so now let's talk about graphing exponential functions. And really, as long as you have an understanding of what that power is, what that exponent is, then this is going to be easy to do. Just make a chart. If you forget what the parent function looks like, you can always go to a chart. Okay, so I went ahead and filled in some of these values. I just have to figure out what 2 to the negative 2 is. That's 1/4. 2 to the negative 1 is 1/2. 2 to the 0, anything to the 0 is 1. 2 to the first is 2. 2 squared is 4. So I filled in the chart. And then I can just graph it. Okay, so you can see over here I've done the same thing. This time I started with the higher numbers first. 1/2 squared is 1/4. 1/2 to the first is 1/2. Filled in the chart. So one thing I want to point out here that these both have in common is this point. So this is something that you see anytime you have that exponential function, one of the parent functions at least, where you don't have any kind of a constant in front. But if you just have an exponent to the a constant to the x power, this point is always going to be on the graph. Okay, so if we've got a function a to the x where a is greater than 1, like 2 to the x, like we were just looking at on the left-hand side of the last slide, that's called a growth function because the numbers keep getting bigger and bigger. So a few things that you should note about growth functions. They pass through the point 0, 1. They're shaped like, here, let me draw it for you. Okay, there it is. I drew it for you. Always shaped like this, a little bit of a boomerang shape, I'd like to say. Here's that point 0, 1 that we talked about. Okay, so now let's talk about end behavior. I'm going to put some arrows there to show we're going on forever and ever. If I look at values as x approaches positive infinity, so x is approaching positive infinity, it's going this direction. What happens to f of x, or the y value? You can see that y values get bigger and bigger, so f of x approaches positive infinity. But if x approaches negative infinity, in other words, if I go in this direction towards negative infinity, well, now I look at my y value, or f of x, and f of x, y value approaches the number 0. Now let's look at a decay function. So that's one of those functions that was on the right hand of that slide 2 slides ago where this is a fraction, a is a fraction, so I keep multiplying by a fraction, in other words, something between 0 and 1, so my y value keeps getting smaller. Okay, so in that case, I've got a, that's the base here, between 0 and 1. Again, it passes through that point 0, 1. Still passes through the point 0, 1. It's shaped like, all right, let's see what happens there. Okay, so here's the shape. I've drawn it. Here's that point 0, 1 that we talked about. But as x values get bigger, my y value approaches 0. It gets smaller and smaller. Okay, and as x values are negative, when x values are negative, that causes me to flip the fraction, which causes y values to get bigger. So that's what it's shaped like end behavior. As x goes to infinity, here we are, x going to infinity out this way, f of x approaches the number 0. Okay? However, if x is approaching negative infinity in this direction, y gets bigger and bigger and bigger, so f of x approaches positive infinity. So here's something you might want to write down. Exponential functions, you can see them in several different ways. Sometimes they're written as y equals ab to the x. Sometimes you see f of x equals ab to the x. You know that those are the same thing, of course. And then you also see them written like this, y equals ka to the x. Okay, I want to point out the difference, though, from a power function. In a power function, x is the base. See, I've got a constant here. B represents a constant, a represents a constant as my base. Here, x is the base. We call that a power function. So that would be something like, you know, x to the 5th or x to the 7th, right? Those are power functions. Okay, and that's not really what we're talking about in this chapter. It's what we were talking about in the last chapter. Those are polynomials. These are exponential functions. So we got a brand new chapter. All right, so these are some problems that we would certainly do without a calculator. And I take something with a base like this and I rewrite it with a different base. Okay, so if I've got 32 to the 3x, then I can say, all right, 32 is 2 to the 5th, and then the whole thing is to the 3x power. And I have to remember, what do I do when I have a power to a power? Well, if I have a power to a power, I multiply these numbers together, which I'm hoping you remember from last year, okay? So if I was going to simplify this, I'd write it as 2 to the 15x, because I'm multiplying those two numbers together when I have a power to a power. Okay, here I've got 1 over 125. If I want base 5 instead, all right, 5 to the 3rd is 125, and then I've got this flipped fraction, right? It's flipped, so I'm going to write this as 5 to the negative 3rd. Hopefully you can see that. That's going to be to the 2x power. And again, when I have power to a power, I multiply the numbers together. So this is 5 to the negative 6x power. Please excuse my handwriting. Okay, so we're going to confirm which functions mean the same thing. Just take a minute for that. Okay, this guy looks like I've got 5, and I could factor out a 2 here, and that'd be 2 times 2x minus 4, right? So it looks like these two have to be the same thing, right? If I'm multiplying these together, that means it's a power to a power. So these two mean the same thing. Now let's look at this one. I've got 25 to the 2x. All right, let's see. That'd have to be 5 squared to the 2x. Okay, so that's 2 times 2x. Okay, over 5 to the 8th. So when I'm dividing and I have the same base, let's think about what we do. We take this number and we subtract the 8. So this is going to be 5 to the 4x minus 8, okay, which we already know now. Oh, look at that. It's the same as that. So what I've got here is all 3 that are equal. All right, let's try a word problem now. Okay, suppose the cost of a hamburger has been increasing at the rate of 9% per year, and it costs $4 now. How much will it cost in 6 years? How much did it cost 18 months ago? Okay, so I've got the cost of a hamburger. It's been increasing at a rate of 9% per year. It costs $4 now. So if I'm going up by 9% per year, then what I have for a base here is 1.09. That's the number I'm going to multiply by each time. Okay, and it costs $4 right now. So that means at year 0, that's my exponent, it costs $4. So what I have to do here is figure out what number do I have to multiply 1.09 to the 0 by to get 4. Okay, well this number is 1, so my starting number then is 4, and I have a function. I'm going to go ahead and erase a, and we're just going to replace that with the number 4. So if I want to know how much it's going to cost in 6 years, well, I have a starting amount here of 4. My function is 4 times 1.09. 6 years from now, I'm going to multiply by 1.09 6 times, so I can just put this in the calculator. So in 6 years, it'll cost $6.71. And if I want to look at what happened 18 months ago, well, now my exponent is going to be negative 1.5. Make sure I'm keeping the same units, and it would have cost $3.51.